It's okay. Start, sir. Hello, sir. Myself, Amogh Mehta. Today, me and my group are going to present on vertex cover problem. Vertex cover problem. The vertex cover problem is a well-known computational program problem in a graph theory. Given an undirected graph, the goal is to find the smallest possible set of vertices such that every edge in the graph is incident to at least one vertex in the set. This set is called vertex cover. Formally, let's denote a graph G is equals to V comma E, where V is the set of vertices and E is the set of edges. A vertex cover denoted as C is a subset of vertices such that for every edge u comma v in E, at least one of u or v is in C. The objective of vertex cover problem is to find the minimum size vertex cover. That is the a vertex cover with the fewest number of vertices. This is known as the NP hard, meaning that there is no known polynomial time algorithm that can solve it for all cases. However, several algorithms in heuristics have been developed to approximate the vertex cover problem and find near optimal solution in practice. Here are few common approaches: brute force, greedy algorithm, approximation algorithm, and integer linear algorithm. The vertex cover problem is an NP complete problem, which means that there is no known polynomial time solution for finding the minimum vertex cover of a graph unless it can be proven that P is equals to NP. There, however, exists polynomial 10 approximate algorithm to find the vertex cover of graph. Now Jay will continue.
Thank you, Amogh. Myself Joy, and I'll be talking about how to solve the vertex cover problem using brute force approach and greedy algorithm. To solve the vertex cover problem using the brute force approach, you need to enumerate all possible subsets of vertices and check if each subset from a vertex cover. Here's the step-by-step process. Enumerate all possible subsets of vertices. Generate all possible combinations of vertices using a suitable method, such as recursion or bit manipulation. Each combination represents a potential vertex cover. Check if each subset covers all the edges. For each subset of vertices, iterate through all edges in the graph. Check if at least one vertex from the subset is incident to each edge. If all edges are covered, you have found a vertex cover. Keep track of the smallest vertex cover. Initialize a variable to keep track of the smallest vertex cover found so far. As you iterate through the subsets, update this variable whenever you find a smaller vertex cover. Return the smallest vertex cover. Once you have checked all subsets, return the smallest vertex cover found. However, it's important to note that the brute force approach has an exponential time complexity of big of O 2 raised to the power n, where n is the number of vertices in the graph. Therefore, this approach is only practical for small graphs. For larger graphs, approximation algorithms are usually employed to find near optimal solution efficiently. Next slide. Now I'll be talking about how to implement the vertex cover problem using the greedy algorithm. To implement the vertex cover problem using the greedy algorithm, you can follow this step. First, initialize an empty set called vertex cover to store the selected vertices. Iterate through all edges in the graph for each edge u, v. If neither u nor v is in the vertex cover set, add either u or v to the vertex cover set. Repeat step 3 for all edges until all edges are covered. Return the vertex cover set as the solution. It's important to note that the greedy algorithm for the vertex cover problem does not always produce an optimal solution. It can result in a vertex cover that is larger than the minimal possible size. However, it is a simple and fast algorithm that can provide a reasonable approximation in practice. Thank you. Now Pranav will continue.
Thank you, Jay. Hello, sir. My name is Pranav Badhe, and I'll be talking about approximation algorithms through vertex cover problem. So there are two types of approximation. One is randomized approximation. Following are the steps of randomized approximation. First, randomly select vertices and check if they form a vertex cover. Repeat this process multiple times and keep track of the smallest cover found. This approach provides a reasonable approximation but does not guarantee the optimal solution. Second, approximation. Select an arbitrary edge in the graph. Add both endpoints of the edge to the vertex cover set. Remove all edges incident to the selected vertices. Repeat this process until all edges are covered. This algorithm guarantees a vertex cover size that is at most twice the size of the optimal cover. Next. So now I'll be talking about integer linear programming through vertex cover problem. So for first we have to formulate the vertex cover problem as an ILP model. We have to define binary variables for each vertex, indicating whether it is included in the cover or not. Uh, we have to add constraints to ensure that every edge is covered. Use an ILP solver to find the optimal solution. This approach can find the optimal solution, but becomes computationally expensive for large graphs. Keep in mind that ILP approaches can be computationally expensive for large graphs due to the exponential nature of the ILP solving algorithms. ILP is typically used for smaller graphs or as a benchmark for comparing the performance of approximation algorithms. Thank you. Now my friend Divyesh will continue.
So I will be talking about, I'm Divyesh Parmar and I'll be talking about the examples. So here is a question in which we have to find a vertex cover for the given undirected graphs. So the first step which we follow is to select a arbitrary edge. In this case, we select the first edge as 1, 6, and then we eliminate all the edges which are either incident to vertex 1 or vertex 6, and we add edge 1 comma 6 to cover. Next step, in the step number 2, we have chosen another arbitrary edge. In this case, we've chosen the edge number 2 and 3, and we eliminate all the edges which are either incident to vertex 2 or vertex 3 in this case. Now, in the next case, step number 3, we select the edge number 4 comma 7 and do the same process. In the step number 4, we are only left with vertex 8, 5, and therefore we get the vertex cover of this graph as 1, 2, 4, 5. Next slide. So here is the pseudocode for vertex cover problem. In this pseudocode, the graph parameter represents the input graph, which consists of a set of vertices and edges. The algorithm initializes an empty vertex cover list to store the vertices in the cover and a visited dictionary to keep track of visited vertices. The algorithm then iterates through each edge in the graph. For each edge, it checks if both of its vertices have not been visited. If so, it marks both vertices as visited, add them to the vertex cover list, and continues to the next edge. After processing all the edges, the algorithm checks for any remaining unvisited vertices. If a vertex is not visited, it marks it as visited and adds it to the vertex cover list. Finally, the algorithm returns the vertex cover list, which represents the vertex cover of the graph. Next slide. The time complexity. The time complexity of the given pseudocode for finding a vertex cover in a graph is big O of V plus E, where V is the number of vertices and E is the number of edges in the graph. So to get this, first step is to initialize the visited dictionary, for which the time complexity comes out to be big O of V. The next step, iterating through each edge, this time complexity takes big O of E. Checking and updating visited vertices takes big O of 1 time, and iterating through each vertex takes big O of V time. Therefore, the overall time complexity comes out to be big O of V plus E. Next slide. So we conclude our presentation here. Thank you for listening to us.